the stress strain carbon tension of a mild steel. So we all know the Hooke's law. Hooke's law. Stress is proportional to strain, and when the stress is proportional to strain, what is it called? Proportionality. Proportionality limit. How can we define graphically? Suppose this is the axis, here is the stress, and this is the strain. If both are increased linearly, that means the first point, suppose this, second point, suppose this will increase linearly. That means if it is x, it is y proportional to x, then there will be a linear relationship. Linear. And this point up to which the linear relationship creates, it is called proportionality limit. And now come to the point. In the stress strain curve, we have to stress strain curve, there is various points of challenge, just like a relationship has. Suppose this is the stress strain curve of a mild steel. Okay. So we have already know that. So this is the stress strain curve, and this point is called linear elastic region. That means at up to this point the stress is proportional to strain. This is called linear elastic region. So A point is called limit of proportionality. Now come to the point B, and you have already known that at which point a proportionality limit ends, limit of proportionality ends. It is called elastic limit. Though, so this part is more important. It here the upper hill point. Here is the upper hill point, and here is the lower hill point. It is the upper hill point. Upper hill point, and here is the lower hill point. And from this region to this region is called strain hardening region. And at this point, look at the point, the peak. There is no specific peak here. It is just like curve. Just ignore the notches here created due to my fault. So here is the ultimate stress, and after that this portion to this portion is called post ultimate region. And now let us come to the specific point of the curve. We have seen that there is the region, there is the region where the upper hill point and lower hill point occurs. This portion is called upper hill point, and this point is called lower hill point. Suppose this point is C and this point is B. So the point B has no practical significance. Point B, the upper hill point, no practical significance. But point C is used for cold working. At this point actually the Fy for mild steel is 250 Newton per millimeter square, and yielding begin from this point. Now let us draw again the line, the portion, the C and the T. The B point is there here, and C and T. and from here the yielding generally occurs. That means from there is no additional forces applied to increase the strain. It is the strain increases automatically, and from point C the strain is 0.12% strain, and at point D is 1.4% strain. And between this point it is called plastic strain. Plastic strain is 10 to 15 times elastic strain. Now this is the point B, this is the point C, and this is the point D, and this is the point E, and this is the point F. So it is upper yield point, it is lower yield point, and this part, this part, this part is called strain hardening hardening region. And at this point materials crystalline structure and atomic structure changes. And this is the ultimate strain, where the strain is 20% of mild steel, and at the fracture point 25% of mild steel. So let's make a summary of this. Suppose this is the graph. This is the graph. Now here the strain is 0.12%, here 1.4%, here 20%, and here 25%. Everything is for mild steel, and This point is called elastic limit. This point is called upper yield point. This point is called lower yield point. It is the point of fracture. Now come to another point, the actual curve and engineering curve. Engineering stress strain curve. So engineering curve is actually about the current condition, the current stress strain condition, and actual is default. So so current, that means at an instantaneous point of time, that means suppose this is the stress strain curve. This is the actual stress strain curve, and this is the engineering stress strain curve. That means actual stress is always greater than engineering stress strain curve. What does that mean? That means suppose a mild steel bar, suppose a mild steel bar is undeformed in shape, in undeformed shape, undeformed shape, and we apply tension over it. So at this point, what will be the, at point t is equal to 0, at time t is equal to 0, what will be the area? Is actually the original area. That means the stress is equal to P by A0. and it is deformed due to tension, and the area becomes this. So this is called actual area. That means sigma actual is equal to P by A A. So here A0 is greater than AA, so sigma actual is always greater than sigma engineering. Now let us suppose so what we have understood, the actual stress is always greater than engineering stress. So what will be the actual strain? Actual strain is equal to L1 L0 to L1 d of engineering strain. That means dl engineering E L0 to L1 ln 1 plus Le is equal to La. The formula is L actual is equal to del L engineering ln 1 plus del L engineering. Another formula is sigma A is equal to sigma 0 1 plus minus del L by L. This is for stress. This is called engineering stress. This is called actual stress. And this positive is negative is called positive for tension and negative is for compression. So let's emphasize on the negative and positive side. We have already known that the actual curve is like that and the engineering curve is like that, actual curve and engineering curve. So here that means at any point, at any point, can you understand the type of force from this graph? The type of force applied on it from the graph. Here the actual stress is equal to sigma engineering stress 1 plus eta. That means engineering stress plus sum of engineering strain happens. So, so this curve is for tensor, and here for compression, this is the engineering curve, this is the actual curve. Because here the formula is, so this is the significance of that sign. So let let's end this conversation regarding the stress strain curve of mild steel.